So today we're going to distillation, our next topic in the what do you call it, subject or in the course. Okay, so let's see what's in it. All right, so I think you've heard about distillation many times since you were in your high school, maybe. Yes, you've heard about what distillation is or not. Today is not the first time. I know when you take mass balance, you already have been given some exposure on what a distillation process is or not. Because I used to teach mass balance before, and I know there is like one topic or one section in the course or in the subject that we have to actually introduce you to all the available or famous or the mandatory ones, the unit operations that you need to know in order for you to be able to do the mass balance, right? But do you still remember what it is? Do you? Jawablah. Janganlah buat saya cakap macam sorang-sorang. You guys. Yes, maybe. Okay. So distillation that you what you have been exposed to in your high school, I think is penyulingan, where you produce isolane, right? But for chemical engineering, the same principle is actually used to separate components in a liquid solution. So let's say if you have a mixture of A and B, two liquids, and A and B have different boiling point, right? So it will be possible for the mixture or the components in the mixture to be separated from each other. So if you have A and B, A is having a lower boiling point compared to B, so you will be able to purify A at the top of the column. That is the concept of distillation or separation using a distillation column. So you've learned about a cooling tower, which is also a column, and you've learned about absorption column. So the next column you're going to learn on is a distillation column or a tower, distillation tower. It's all a column. It's a vessel, okay? But it has a different principle of work to make possible the separation between the components in the mixture. Okay, so it's written here in your lecture notes where distillation is separation of different components in a liquid solution. So from the explanation just now, you see that this is possible through the different boiling points between the two or more components in the mixture. Okay, so it involves producing a vapor from a liquid by heating the liquid in a vessel. So that is a distillation column. Okay, wait. All right, so for example, if you have a mixture of ethanol and water, and you know the boiling point of ethanol and water are very different. Ethanol has a lower boiling point compared to water. It's an alcohol, right? So you will know for alcohol the boiling point is very low. That's why it can vaporize really easily and dry up your the surface of where it touches. Okay, so if you heat up a mixture of ethanol and water, what you have in the vapor phase, we will have a higher concentration of ethanol, and the liquid phase that is left behind will be having a higher concentration of water, which is the least or the less volatile. Less volatile means the boiling point is actually higher than the other component. Okay, And there are actually two methods of distillation. The first one is called rectification or fractional distillation with reflux. So rectification is also a distillation. Fractional distillation is also a type, the same thing, and it's also called distillation with reflux. So in these types of configuration, part of the vapor is condensed and returned as a liquid coming back into the vessel. I'll show you the diagram or the schematic drawing of a column, not like this. Okay, this is what you have in your lab during your high school, during your SPM. This is what you learn about, where you hit this vessel, okay, but what do you call it, round bottom flask. So you heat this up, the liquid in here, and you will get the vapor, and the vapor will be condensed, and you get the pure component of a less of the less volatile component. So in this case, if you have, let's say, a juice, fruit juice, you heat up until the boiling point of water. Water will come out here as vapor, and it will be condensed, and you can collect the water here. It's actually quite pure. Okay, and then you will be left behind with a more concentrated solution here, because the water component is actually lesser than where it starts from. Okay, so this is a simple setup of a distillation process. This is actually called a batch distillation. There is no number of stages or whatsoever. There's no reflux as well. So this is not what we are going to learn in this part or in this topic. This topic is more towards introducing you into what we use in the chemical plants to do the purification as well as separation of components in a distillation column. Okay, so the first method is called rectification or fractional or distillation with reflux. The second one is this is the first one, where you can do it through a column. And the other type or the other method is when all the vapor is removed or is condensed as product. So there is no reflux. I'll show you what a reflux is in a while. I have to turn on my battery. It's going out. Because I've been using it in the convocation hall. So it's now running out of battery. Okay, done. All right, so the first one is with reflux, and the second one is without reflux. I'll show you what the reflux is in a while in this schematic. Okay, so if you see here, sorry. Okay, this is how you draw a distillation column. This is a tray column. For distillation, it's just quite the same as absorption, where you learn on how to design a tray column as well as a pack column. This goes for distillation as well, where a distillation column also can be a tray column or it can be a pack column. So the first, in this first few early topics, early parts in the topic, we will do a tray column. Okay, so if you see here, this is a column, and you will have a feed flowing in. So this feed is actually a mixture of the liquids. Okay, if you have a binary mixture, then it will be two components. If it's a multi-component mixture, you have more than two. Okay, if it's more than two, you already call it as multi-component distillation. So this is the feed input into the column, and it's put not just about anywhere. It's actually, there's a careful calculation of where your feed plate should be. Okay, feed tray. So if you see here, these are trays. So tray number 1, tray number 2, number 3, number 4, 5, 6. So if you see the configuration here, you have the first tray up here, and you will have what we call a weir over here. Okay, a weir will be dictating how much liquid will be retained on the tray. You cannot have too much liquid on the tray, otherwise the vapor cannot get through. If you have too little, then you will have a brief contact between the vapor and the liquid, and that is not good as well for the mass and heat transfer. So this the height of the weir here is very, very important for the manufacturer or the designer to decide on. And then when the liquid is higher than the weir, it will flow out and jump into the next plate downward. Okay, the section above the feed plate or the feed tray is called a rectifying section, and the section below the feed tray is called the stripping sections. Okay, so the stripping section will be having a few trays, and the rectifying section will be having a few trays in it as well. And this is a reboiler. It's called a reboiler because you'll have a bottom product over here, and it will be boiled into the temperature that you set, and it will go back into the column, and then it will be a loop without stop. Okay, so if it's a boiler, it will not go back in there. This is a reboiler because it's going to be heated again and again using this boiler. Okay, and from the top here, okay, when you start this column, when you start the operation of the distillation column, you don't have the reflux yet because you don't have the vapor. Okay, the first thing that you want to do is you want to heat up the liquid that is at the bottom of the column, and then once it produces some vapor, it will go up, which is displayed here in the red arrows. So if you see, all the vapors are going up. At this point of time on the tray, there will be no liquids yet, right? So only the vapor are coming up because there's nothing to condensate them in the or in the column. So the vapor will keep going up until it goes to the condenser here. So at the startup of the column, there will be no reflux yet because you don't have enough vapor to be condensed and brought back into the column. So you have the vapor over here, and once you have those vapor, it will go into the condenser, and here you will have a setting on what your reflux ratio would be. Reflux ratio is a ratio of L over D. So R, let me get my pen. Okay, R is called reflux is called R. R is actually L over D. So what is L? That is L, and that is D. So you want to have a ratio of what's going back into the column to the rate of flow rate that is taken out to be your product. So this is your purified, less volatile component. Okay, so if you have a mixture of A and B, A is less volatile than B, which means A will boil at a lesser temperature than B. So you will have a vapor of, you will set the temperature just to boil A. Don't set the temperature so that it will boil both A and B. You have to set the temperature to only boil A. So let's say you have A and B. Temperature of boiling point of A is 60. Boiling point of B is 100. So you will set the temperature to be in between these two temperature, because you don't want to put it on the dot as A, because you will be afraid that not all of the vapor will be produced from your component. So it will be set between the value of 60 to 100, but you don't want to go be above or higher than 100, because otherwise you will get both A and B in the vapor. All right, so once you've got enough condensed vapor, what's going out here there is called V, which is vapor. Once you have enough condensed vapor with a full or partial condenser, you will be returning a ratio of the flow rate there to go back into the column as reflux. So when you have the reflux going into the column, then only you will have a collection of liquid on the first plate. And then the liquid will flow down through the openings on the plate. So if you see, it will not flow here, sorry. The liquid will not flow here, but instead the vapor will go up from the opening or the holes. The liquid will fall from that weir. But you want the vapor to be able to flow or to go through the liquid that is retained on each plate. So that's why the configuration is very important, and you don't want the tray to be flooded with the liquid. So why do you need to have the reflux? Why do you think, from a logical point of view, why do you think you need the reflux? Anyone can have a guess on why actually you need. Anyone want to volunteer? Or otherwise I'll call names. Anyone can have a guess. Don't worry to be wrong. It's okay. So why do you think you need the reflux flow coming back into the column? Leong Kai Siong said to avoid wastage. No, not to avoid wastage. Any other suggestion? Improve. Leong Kai Siong said to avoid wastage of the compound. Tan Yongshan said is to improve the purity of distillate. Pu Wen Ji said is to continue distillation. Okay, keep it coming, everyone. Guess why do you need the reflux flow? We have 3 answers here. I want more of you answering in the chat box. Why do you think you need the reflux? Other than all these guesses from your friends. One is to avoid wastage. The next one is to improve the purity of distillate, or to continue distillation. Lagi? Mana lagi tekaan-tekaan bijak you all ni? To increase the efficiency of distillation. Okay. Ada dah. Tu je tekaan-tekaan you guys. To maintain temperature profile. Interesting. Okay. Shafiq Adli. Okay. Anything? Any other answers? Come on, guys. Cepat jawab. Nanti you all nak buat video ni, you need to know why. Any other guess? Any other guesses other than these 5 answers? Okay, so from these 5 answers, to maintain liquid quantity on tray from Nizam. Interesting, there's some truth in it as well. So from here, I think I saw 2 correct answers. The first one is from Tan Yong Sheng, where he says that it's to improve the purity of distillate. Why do you think so, Tan Yong Sheng? Can you explain? Turn on your mic and explain. Why do you think it's to improve and why do I say that it's true?
Because when when the first distiller is out, you after undergoing the reflux process means that it will be going through another distillation, so more impurities will be removed during the process.
In a way, okay? In a way. But actually there's a process of mass transfer in between. But great and very good that you can think of a way to explain why you think it would be to improve the purity of distillate. And Shen Long, you said to increase the efficiency of distillation. Efficiency in distillation is quite different. The reflux is not to increase the efficiency, but you can adjust the reflux ratio to increase the efficiency of your column. Okay, so if you have a reflux ratio of 1.5, let's say, and you adjust it to 1.7, it will have different efficiency. Okay, but the reason why we need to have the reflux, not that we can adjust the reflux. This is comparing between having a reflux and not having the reflux. Okay, so not having the reflux, of course, is the least efficient process compared to the one with the reflux. And Shafi Adli said to maintain temperature profile. Okay, how do you why do you say so, Shafi Adli? Why do you say to maintain temperature profile? Shafiq, boleh explain or you just like teka-teka je, you think it's something to do with the temperature? Tak ada dah Syafiq. Janganlah takut. Bila saya panggil tu maksudnya saya sayang tu. Ha, jawablah. Jangan takut. Don't be afraid to be wrong. Okay, don't be scared. Sorry, tak dengar.
Can you hear me?
Yes. Oh, mic
Yeah,
problem
right. Okay.
tadi.
Because I think throughout the column,
Mm.
the temperature is not uniform.
Throughout the column, yes, the temperature will not be the same because you have a reboiler here and that is the only heat source in the column, right? So it will be the hottest at the bottom and it will be the coolest at the top. So if you have the reflux coming in, it will not to mainly to maintain the temperature profile because what we have to maintain the temperature profile is by the reboiler. Okay, so it's good that you are thinking towards the temperature as well, but I will explain to you how it works in a while. Okay, Nizam, why are you saying to maintain liquid quantity on the tray? Can you explain your thoughts?
Because I think
Mm.
when for example, when component A is vaporized, then it will condense. So at some point,
It'll be out of liquid.
if there is not enough liquid on the tray, so the reflux can maintain the liquid on the tray.
Yes, that is quite right as well. So Tan Yongshen says to improve the purity of distillate, right? And the mechanism is by maintaining a certain liquid quantity on the tray. So very good. So you have the reflux coming in to have some liquid on the trays. Why do you need some liquid? Okay, it's like this. You have A and B in the beginning, let's say, and then you heat it up. When you heat up The one that's turning into the vapor is A, because A is less volatile, right? So when A vaporize, okay, when A vaporize here, okay, it goes up until it's condensed, and then you will be having less A here, right? Because A already vaporized. And A will also bring some B with it. It's not 100% separation, will bring some B in it. So let's say it will bring up there up to 80%. This is not definite, okay? This is like an assumption based on the volatility of A. Okay, let's say when the first V that comes out is equals to 80% pure, 80% A, and the other 20% is B. So what you want to do is you want to increase this from 80% to 99.9% A. So this is usually what they target for in a distillation column, right? So the way for you to increase is to bring back this liquid, okay, that is condensed. This liquid, which is rich in A, goes back into the column. Now, what you have on this tray over here is a liquid that is richer in A. So once the vapor that is penetrating through the opening of the tray goes through the liquid here on the plate, there will be a mass transfer. A mass transfer of what? A mass transfer of the vapor coming up. It will be richer and richer and richer in A because it's transferred into the vapor. Okay, so that's how you are going to increase the 80% to the percentage that you want. So the more plates you have, the purer, or the higher the purity of A that you can get. Do you get that? That's why you need the reflux ratio. If there's no reflux, then it would be a flash distillation. You don't call it a distillation column. It will be called a flash distillation, okay? Sometimes a flash distillation do have some plates, but there's no point of having a plate actually if you don't have a reflux coming back into the column. So if it's a flash distillation, you will be heating the liquid and flash it, and you will have the vapor coming out here, and it's condensed and taken out right away after it's converted into the liquid. So that is a flash distillation. So if it's like this, the configuration that I'm showing here, this is called a distillation tower, or a distillation column, or rectification, or fractional distillation, or distillation with reflux. All right, so a careful calculation needs to be done in order for you to get the right height of the tower, the right number of trays, the right cross-sectional area, the right temperature for you to run your distillation column. All right, so this D is called distillate. Okay, this V is vapor. L is just the liquid coming in as reflux. Okay, so it's called L. F is the feed. Okay, so what you mainly will learn in this course is to design the number of trays that you need to do the perfect separation, or to do the separation that you desire or instructed to do. And W is the bottom, what we call the bottom product. So remember all these names or terms: bottom product, distillate, reflux liquid, vapor, and feed. Any question before I go into the calculation? Ada soalan? Okay, this is the principle, how it works, the distillation column. All right, so this is how it looks like, the distillation column in the chemical plants. So these are all the types of distillation. You have simple, you have fractional, you have steam, immiscible solvent, azeotropic, extractive, vacuum, molecular, and entrainer sublimation. So what you will learn in this topic is only simple, fractional, and steam distillation, I think. Only those. And we will not be covering all this. Alright, so those are the different types of tower that you have. So this is an example of a fractional distillation in the petroleum processing plant or oil refinery. Okay, so before we go into the designing of how many trays you need to do a certain separation, you need to understand what Raoult's law is. Before this, you have been taught on Henry's law. So anybody can remember what Henry's law is? Cuba tulis dekat chat box. So what is the equation for Henry's law? Can you write down the equation? Let me see your equation for Henry's law. Do you remember? Ingat tak equation for Henry's law? Kau tak ingat dah? You don't remember anymore? What's the equation? What is it relating between what and what for Henry's law? Don't you remember? Semua tak ingat dah? Tak ingat cakap tak ingat. Cakap don't remember. You don't remember anymore. Cepat. Kalau tak ingat cakap tak ingat. Kalau ingat tulis the equation. Over there. Ingat tak? Yang mana satu ni you guys? Elma, Melissa. To everyone. PA equals to HXA. Okay. So you have a relationship between the partial pressure and the liquid composition. And then you can relate the liquid composition to the gas composition. The next equation would be, you will use this equation as well, right? EU over P to relate between the YA and XA. So this is Raoult's law. If you are looking at, thank you, Elma. So for Henry's law, you have Henry's constant. Okay, you have Henry's constant. Okay, so for a Raoult's law, you don't have a Raoult's law constant, but you will see that the Raoult's law is actually a relationship between the vapor pressure and the partial pressure. Okay, so the partial pressure is actually equals to the vapor pressure of A times XA. So don't be confused with the capital P and the small p. The small p is the partial pressure. Okay, this one. The capital P is the vapor pressure of pure A. But the capital P alone without A or B, that's actually the total pressure of the mixture. Right? So not only you have partial pressure that has A over there, you also have vapor pressure having the component over there too. So be careful. PA is not total pressure, it's the vapor pressure of component A. And XA and YA is like usual, the mole fraction of A in the liquid for XA and the gas for YA. So this is the a more detailed picture or diagram of what happened on one tray. So if it's like this, it's normally a bubble cap tray. So you have a bubble cap tray. You have a sieve tray and many other types of trays. You can look it up in the internet to see how many types of trays are available in the market right now. So like I said, you will have your liquid flowing down here, okay, and then this liquid is actually denoted by the blue wave, okay, the blue wave over there. And then the white arrow is actually bringing the solute up. And because this one is already touching or in contact with the liquid or mixed with the liquid, the composition of A on the plate is going to be higher. So from the bottom plate to the top, it would be increasing. The concentration on this tray would be higher from the tray below it, and so on until you reach the top of the tower. Okay, so that is what's said. Sometimes not sometimes, this Raoult's law is actually the same as Henry's law. It's used to relate between X and Y, because what this equation is relating or is only the partial pressure and the vapor pressure, and from the common equation of partial pressure of A over total pressure is YA. So you will relate that equation. You will change the PA into vapor pressure over total pressure. Okay, so you will put this equation into this equation, and you will finally get YA is equals to PA over PXA, and you will need the vapor pressure to do the calculation. Okay, so if you use the partial pressure, you cannot relate it to the X. So if you only use this equation, you can only relate the partial pressure to the X. And if you use this equation, the partial pressure to YA. Now you want to relate between YA and XA. That's why you use both equations to manipulate them, and you will finally get that equation. Okay, and you'll be using this equation when you are designing or doing the calculation. So that is Raoult's law. Okay, let's see now the vapor liquid equilibrium. You have to get to know what is vapor liquid equilibrium. Have you heard about vapor liquid equilibrium before? In any other subjects, have you been introduced to it? Have you been introduced to VLE before? Yes or no? Senang di soalan tu, yes or no? Yes, okay. In which subject? Mass balance as well. In mass balance. Okay, thank you. So, do you actually understand what a VLE is? A vapor liquid equilibrium diagram is. Do you actually know how to read it? Do you actually know how it's produced? Yes or no? I'd like to see some response in the chat box. Do you know the principle, or do you know how to read the VLE diagram? Tahu ke tak? Cuba jawab dengan suara juga. Aku tak nak type kat situ pun. Petang-petang ni semua orang nak tidur because you've been on a break for a week. Not everyone is asleep. Ya ke? Are you asleep? Cakap yes or no? Still in holiday mode. Are you asleep now? So I want you guys to tak tidur tak ngantuk Iza. Bagus ni Iza. So anyone that is asleep now, you stand up and breathe some air into your lungs. Take some breath. Cepat now. Stand up and inhale, exhale for 5 times, so that you be opening your eyes. Okay, you forgot already what a VLE diagram is. Okay, that's okay. So now I'm going to explain to you, because you're going to be using this diagram a lot. Okay, you'll be using a VLE diagram as well as the XY plot here. All right, so what you have, this is called vapor liquid equilibrium. You actually produce this using a VLE apparatus. Okay, you will be using the VLE apparatus in our separation processes 1 laboratory. You'll be doing it a lot of experiments to actually produce your own VLE for methanol water mixture. Okay, so this is for benzene and toluene, I think. Okay, benzene toluene mixture. So your A, which is the more volatile component, your A is always the more volatile component. Okay, comparing benzene and toluene, toluene would be your your more volatile component, or with less or lower boiling point. How do you know between benzene and toluene which one is the more volatile component? If you have to make a lucky guess or a smart, intelligent guess, how do you actually guess which one is having a lower boiling point? Okay, how do you know? How do you guess? Or what principle do you want to use to say that, yes, Azwan, the more volatile component will be having lower boiling point. But how do you know which component will have a lower boiling point? How do you know which component between the two will have a lower boiling point? If you have to guess, number of chains, okay? Number of bonds, if that's what you mean, okay? So covalent bond or van der Waals bond. All right, so that's nearly true, but the simplest way to know which one is having a lower boiling point is by the molecular weight. You look at the molecular weight between benzene and toluene. Benzene will have a lower molecular weight, so therefore it is having a lower boiling point, and it would be the more volatile component between the two. Okay, so you always look at the molecular weight of the molecule to guess. Okay, so all right, so let's see how you produce this VLE diagram first, and then we'll go into the XY plot. Okay, the VLE diagram is produced, for example, in this case, is by heating the mixture of benzene and toluene. Any mixture that you have, okay, for this particular mixture, okay, you don't even know what the composition is, or you know what the beginning composition. Now you heat the mixture of the benzene and toluene mixture, and this is the original composition before you heat it up. Okay, so it's having 0.318 mole fraction of benzene. So when you heat it up here in the liquid, the XA1, or the initial composition, is 0.318. So you heat the increased temperature until it reaches this temperature. You will have the first vapor formed. You will see the first vapor. Okay, so this first vapor will be seen at 98, or not will, when you do the experiment, you saw the first vapor was formed or was produced at the temperature of 98 degrees Celsius. So you pun tanda 98 degrees Celsius, and this is x1. You get the first point over there. Okay, and then this vapor that you get, you will go and condense. Okay, condense the vapor and it will become liquid. You will go condense the vapor, it will become liquid. So what happened during condensation? The temperature will not change because there is a change of phase from the vapor to liquid, right? So, but what you found from the condensed vapor, you condense vapor and then you measure the composition. Okay, you measure the composition when it's condensed, you get YA1, which is 0.532. So you put under 0.532 over there, right? So you have this at 98 degrees Celsius, you akan buat satu line panjang at 98 degrees Celsius. Now this is your YA1 start. Okay, you pun dapat that point. And then you condense, you dapat another point. So you ke sini where it meets, you get the point for the saturated vapor line. And the first point would be the point or 1 point for saturated liquid line. Right? So you have to repeat this from 0 to 1. So maybe you want to do it for 20 or 0.2, you want to do it for 0.4, you want to do it for 0.6, 0.8. Okay, and you have to repeat with all those mole fraction or initial mole fraction and see at what temperature it will produce its first vapor. Pergi condense lagi and then condense, dapat berapa dia punya composition. And you have to do this over and over again for a few points on the graph so that you can make the saturated liquid line, okay, from the temperature where you saw first vapor, and then the saturated vapor line where you see the first liquid, or not the first liquid, the composition of the liquid from the condensation for each initial composition. So you will have those two lines forming a shape like forming a leaf-like shape, a shape like leaf. Okay, so that is how you produce the VLE diagram. And if you see the distance, okay, the distance, there's actually a distance between equilibrium line and this one is for this one, the XY plot. This one is for the XY plot. All right, so first from the VLE experiments, what you are going to get is the VLE diagram, which is this saturated liquid line as well as the saturated vapor line. Okay, from this VLE diagram, you can transform it into an XY plot. How do you transform? You will read the X1 and XA1 and YA1 for each experiment, and you will plot the points on this. So this is actually an XY plot. There is no saturated liquid line. There is no saturated vapor line. It's just a relationship between the X and the Y, which means if you hit a liquid with 0.318 composition or mole fraction, if you heat it up, when it becomes vapor, you will have a vapor or a condensed vapor with a composition of 0.532. So you can read along the lines over here, maybe with 0.6, for example. If you start with 0.6, what you will get is a liquid with 0.8 benzene in it as a result. So what you want it to be is you want to achieve as far as possible or as higher as possible for the purification. Okay, so for this XY plot, the distance between equilibrium line, this is what we call an equilibrium line. Okay, the SY plot is an equilibrium line. The distance between this line to the 45-degree line, this is 45-degree line. Okay, this is the distance between the two lines. Okay, the bigger the difference, the easier is the separation. Which means the bigger the distance between the 45-degree line and the equilibrium line, actually you will have easier separation. Okay, if you ada line yang dekat dengan each other, kurus saja macam ni, then the separation is going to be quite difficult. Alright, so those are some explanation on what a VLE diagram is, as well as an XY plot. So you cannot produce the XY plot without the VLE diagram. So you have to produce the VLE diagram first in order for you to get the XY plot. And for mixtures in the world, most probably the VLE diagram is already there, already existed, and as well as the XY plot. Okay, so now, so that is like a normal VLE diagram, but you have some non-ideal systems, okay, which will present more difficult separation. This one is when the shape is like that. I think this is with ethanol, I think. Not too sure, but you have to check. This one also quite hard to do, and these are usually called, this is non-ideal, okay? So as for the two bottom ones over here, these are called azeotrope, which means if you heat this up, okay, with this XY plot, you will get the maximum of only not more than 0.7, I think, the purity over here. That's all you can get, because there's already a point there where you cannot really, when you heat this liquid, the vapor produced from the liquid will have the same composition, so you cannot do further purification. So the maximum it can go according to this diagram is approximately 0.7. That's the highest purity that you can go with a more volatile component. Right, so let's see. Oh, before we go into the designing of the tray, now let's see the relative volatility, which is alpha value. Before you do any designing, you need to know the relative volatility of each of your component. So you want to see how more volatile is your component A with respect to component B. So you need to do some calculation where YA here is mole fraction of A in the gas phase, XA is the mole fraction of A in the liquid phase as usual. Right, for an ideal system, this is what you always use for the alpha value. You just take the vapor pressure of pure A over the vapor pressure of pure B, then you will get your alpha value. If your alpha value is bigger than 1, then separation is possible. If it's less than 1, then it's not possible. Okay, so alpha EB is how to separate. So this is how you decide whether the distillation column is actually possible to be used as a separation machine or separation means for your mixture. Okay, so that's relative volatility. So now we'll go into the designing of a single phase equilibrium, not designing. This is just basic principle, not to design the number of trays yet, okay? I want you to know how to do some simple calculation first. But first, before we go further, I would like to introduce you to the nomenclatures or the symbols that we use in distillation. So it's quite the same as absorption. I think you will have L naught as the liquid coming in, right? This is for one tray. If you imagine for this tray, okay. So what's pictured here is one tray. Okay, this is not to design yet. This is just to decide or to calculate on one tray what would be the composition. Okay, so for this one tray, from the horizontal, it is transformed into from vertical, sorry, from horizontal laid plate. Now it's like vertical laid, but the flow is going to be horizontal. This one, the flow is vertical, but this one the flow is horizontal. So you just imagine the V as the vapor, V2 coming up. Okay, this is only, you have to imagine this for one tray only. So let's talk about this tray. So you have V2, let's say, and then you will have V1. Okay, because this is tray number 1, for example. Okay, so this is tray number 1, and then you have V1 over there, and you will have L naught that is coming in, and then L1s, because this is tray number 1. So if this is tray number 1, the tray on the top is at the top is tray number 0. So this is not appropriate actually. So what we want to do is to take out all this and just imagine that there's another tray down here. Okay, so if this is tray number 0, this is going to tray sorry, this is tray number 1, so this is 0, and this is going to be 2. 0, 1, 2. So this is L naught because it comes out of tray number 0, and this is L1 because it goes out from tray number 1. This is V2 because it's like it's coming out of tray number 2 and goes into tray number 1. So this is how the symbols are put together for the diagram. Okay, but if you are quite lazy to remember the reasons behind it, because I am a person who has to know how things are, or the principle of each of everything, so that I can remember it longer in my head, not just memorizing. Okay, so this is inputs, 2 inputs and 2 outputs of the tray. Okay, imagine the tray being arranged vertically like this, and all your liquid coming down and your vapor going up. So you have 2 inputs. Okay, we have to assume constant molar overflow, where it says that V1 is equal to V2. There is no loss of V, and there's also no loss of L. So first, as usual, you'll start with a total material balance. Okay, input plus input equals to output plus output. Okay, so you do the balance on A by putting in the composition of each flow rate or each stream. Okay, so now if you look at this equation over here, what you normally have is the initial values of L naught. You can set that. You know the composition for the liquid, and you know the flow rate and composition of the of the vapor coming into the column. And For L1 and V1, from those assumptions, you can use the same value because we are assuming constant molar overflow. Okay, the only things that you have to calculate are V1, sorry, XA1 and YA1. So you have to solve this simultaneously using a graphical method. So I want you to take out your graph paper now. Okay, we will do example 11.21 together. Okay. So cepat. Are you ready with your graph paper? Buku saya, my book is at home. Are you ready with your graph paper? So look at 11.21. 11.21, yeah. Let me search for the book. The June Copley's book. Are you ready with the paper? The graph paper? Go get your graph paper. Go get your graph paper together. So let's look at apa saya nak cakap tadi? Nak ambil buku June Copley's. Transport processes. My laptop is not responding well. Okay, in which page tu? Siapa dah buka buku June Copley's example 11.31? Example 11.21, sorry, 11.21. Dah buka belum? So what's the question? Too high. Okay. 650. Okay, now we'll go into distillation. Can you look at the example? The example 11.21. Okay. So what you have here is a question. Is everybody still there? Who am I talking to? Are you listening to me at least? Are you listening? Yes, don't be sleeping, okay? This is important. Okay. So let's see. I know you cannot see my you cannot really see my PDF, right? So I'm going to copy this question. So let's put the question over here in this slides. So example 11.2, this one. Okay, let's see. You can see the question, right? So the question says, a vapor at the dew point of 101.32, this is the dew point, and containing a mole fraction of 0.4, 40% of benzene, 60% of toluene, and 100 kg mole total is contacted. Okay, this is the mole, the number of moles. Contacted with 110 kilogram mole of a liquid at the boiling point, containing a mole fraction of 30% benzene and 70% toluene. Okay, the two streams are contacted in a single stage and the outlet streams live in equilibrium with each other. Assume constant molar overflow. Calculate the amounts and composition of the exit streams. So you need the composition as well as the amount of the exit streams. So this is what happened. You have a vapor of having 40% benzene and you have a liquid having 30% benzene, and you have the flow rate for both. Okay, you have the vapor flow rate as 100 kilomole and you have the liquid flow rate as 110 kilomole. So what you want to do is you want to assume constant molar overflow. So straight away, you can just assume V1 equals to V2, L0 equals to L1. L1 dengan L0, V1 dengan V2. So first we will do balance on A. Okay, put all the numbers that you have. Okay, these are for the inputs. Now for the outputs, because of the constant molar overflow, you have 110 and 100 as well for the V and the L. So now what you are left to find is only XA1 and YA1 because you already got the amount of the flow rate, the amount of the component. Okay, so for L1 the answer is 110. For V1 the answer is 100 kilomole. Okay, so now you want to do a trial and error to get XA1 and YA1. Have you got your equilibrium line ready? I mean your XY plots. Do you have your XY plot ready with you? So take your graph paper. Take your graph paper. Wait, the question is benzene toluene? Or yes. Go to your appendix and find the equilibrium data for benzene and toluene and please draw the equilibrium line first. Draw this line below. You must draw from 0 to 1 and 0 to 1 with the same scale. Okay, remember this? Your x and y axis must be with the same scale. So it cannot be longer looking for the y-axis but shorter for the x-axis. Cannot. It should be the same length for x and y. Same scale. Okay? Are you drawing the equilibrium line now? Yes or no? Are you drawing it? Okay. Draw the equilibrium line now. And I want you to do this trial and error together. How much time do you need to draw the XY plot? Give me a number. Cepat, berapa minit nak untuk draw the XY plot? Give me one number. Yongsheng, berapa minit Yongsheng? You need to draw the XY plot. Yongsheng? 15 minutes. Oh, lamanya. Equilibrium line je pun. Remember to use the same scale, yeah, X and Y. Yeah, X and Y. I'm giving you 10 minutes, okay? 10 minutes. So now it's 3:25. I'll be turning on my mic again at 3:35. You have 10 minutes to draw the axis, okay? So everyone, hi, you should have your XY plot ready by now. Do you have it done? Yes? Yes or no? Because I'm going to start the trial and error now. Okay. So now I want you to take a value of other than 0 0.2, 0 0.4, or 0 0.3. I want you to take the first value to be not 0 0.2. Okay, because if you take 0 0.2, then you go to the equilibrium line, 0 0.2, then you will get a y of 0 0.51 on your graph paper. But now I want you to take a value of not 0 0.2. You can go 0 0.25, 0 0.15, 0 0.28, up to you, your own value. And I want you to write down your value, what your XA1 is, and what do you get for your YA1. Okay, now write down in the chat box, what do you get for your corresponding XA1. And you have to write down what XA1 that you take and what is the YA1 you get. Okay, anyone? Anyone done with it? So write down here in the chat box if you have. Sorry, guys. Okay, you take this XA1, you put into the equation, sorry. So you take the equation, let's say you take 0 0.2, you put into the equation here, and you will get your Y1 to be a certain value, which is 0 0.51. So that's when you get this point. Sorry, where's my pen? With 0 0.2 here, 0 0.2, when you calculate, okay, with this equation, you will get 0 0.51. So this is 0 0.2, sorry. Bukan dengan graph, sorry. Not with the graph, with the equation first. So let me show you. This is 0 0.2. Okay, what you get is 0 0.51 for that point from the equation. So this first point is 0 0.2 and 0 0.51. Sorry. Terbagi ajaran sesat pula kat you guys ni. Okay, so if I want you to take a value other than 0 0.2, maybe 0 0.18 or 0 0.15, a value that is easy for you to plot on the graph. Okay, so when your XA1 is 0 0.1, your YA1 is 0 0.62. That's Tan Yongsheng's point. So I want you to plot that point, Yongsheng, on your graph paper with X of 0 0.1 and Y of 0 0.62. Okay, so you will get 0 0.1 and 0 0.62 somewhere there. So that's going to be your point. All right, so I want you, okay, the point now is to have a straight line that crosses the equilibrium line. So now you take a value of 0 0.2, you get a point above the equilibrium line. Now I want you to take another point that will cross the equilibrium line. So according to this, it's taking a value of 0 0.4. So you will calculate from the equation to get y of 0 0.29. So I want you to take a value near 0 0.4, not 0 0.4, but near 0 0.4, whatever value you can easily plot on your graph paper. And write down what is the value of your XA1 and your YA1 correspondingly. Cepatlah. Lambat sangatlah you all buat calculation. Oops. Okay, the next XA1 berapa? Yang Sheng, what do you take? Okay, when 0.35 for your X, you will get 0.345. 0.35, somewhere there, and 0.345. So you get another point. Just to check whether your line is a straight line or not, you will take another line or another point to get your straight line done. But actually 2 points is 2 points already enough because this is a straight line. But if you want to do another point, then you get all those 3 points aligned and you make a straight line. But the point is to get a straight line that crosses the equilibrium line because you want to be reading that XA1 and YA1. So I want you guys to tell me what is your answer from the exercise over here. What's your XA1? What's your YA1? From your straight line. Do you understand what you should do? You should use the equation here to find YA1 for each XA1. You have to use this equation. Wait. This card there. Okay. So after you've done that, you want to take a few points to get a straight line over here. You want to have this straight line. So in this case, it's using 3 points to get that straight line. And when you have that straight line formed, you will be able to get the point where it crosses, where your line crosses your equilibrium line. So write down what is the value that you get from the exercise in the chat box. Cepatlah you guys. Penatlah saya cakap dengan you guys ni. So if you draw your graph correctly, you should get XA1 of 0.25 and YA1 of 0.455. If you draw your graph correctly, do you manage to get the same answer with the book? Yes or no? Give me a thumbs up if you do get the same answer as the book. Otherwise, you've done it wrongly and you have to do it again. Okay, Tanzakai, Jermaine, you're done. Okay, that's okay, Yongchen. I think your answer is correct already. Not that wrong. It's already near or more accurate, I think. For X, you are more accurate. I mean, with more decimal places. For Y, you have less decimal places with the answer that you have on the slides, but that's okay. I think if you have 0.25 and 0.45, it's already okay. So, do you manage to get this? Cepatlah jawab semua. Yes or no? Cepat, cepat. Kita nak habis kelas dah ni.
Yes, Doctor.
Elma, okay. Elma is okay. Wenji is okay. Iza okay. Good. Nang Kai Siong is okay. Zikri okay. Ainul Naim, Adila, Asri, Amir, Daniel, Amzat. Okay. So, just take a picture of I think for assignment submission, okay, I'm gonna form a Telegram group because otherwise it's gonna be using a lot of my space. Okay, I'm gonna go and form a group. How do I form a new group? Okay, I wanna add Yongsheng. I add Yongsheng first. Okay, Yongsheng. Do you all have telegrams? You all have telegrams? Yes. Yongsheng, is yours Yongsheng 1608? Is it? Is that you? Is that you, Yongsheng? Yongsheng 1608. Or
I'm not sure
I
whether
think
it's me.
yeah, you're not sure whether it's you. I'm gonna add my husband into it and then I'll kick him out. So I'm gonna do SETK 3323 2021. So I'm gonna give you the link. So everyone, please. How do I add member? Invite group via link. Copy link. So now I put the link into WhatsApp. Our WhatsApp group. Okay, join that Telegram group. Use your your name, your true name, not nicknames. Otherwise, I won't know which one is you. Okay, and then upload it into the Telegram. All your graph today. Okay, so upload your graph today. How do I remove? Delete. Is delete contact the same as remove a person from the group? Risau pula saya jadi delete pula nanti. Is it the same? Who's familiar with Telegram? If like you go to the member of the group and then how do you remove? You press delete contact, is it? Betul ke? Siapa yang familiar? Sebab kalau WhatsApp dia panggil remove from group, isn't it? Takut je bila kita letak. Tak apalah, nantilah. I'll just ask Dr. Zaki to go out himself. So you are all now in the group. Okay, so you just take a shot or take a screenshot or scan of the graph that you drew today and upload it in the Telegram for submission. Okay, we'll use that Telegram for submission only, and other communication for classes or tests, we will be having that in WhatsApp group just to minimize my storage, okay, in my phone. Tak do. Azrin, you don't have Telegram, so I think you have to download. Azrin ni is a she ke he? Azrin? Mailing, you have to...
She, her, doctor.
She, okay. So Azrin kena download Telegram, mailing kena selalu guna. Yeah, you don't have to always use the Telegram, just use it to upload. Okay, so by today, okay, I mean by today, when I say by today, you do understand it's by before midnight, for you to upload your graph that you did today for this exercise, because I want everyone to be doing this, otherwise I know some of you will not do. This is just like having the class together with you. I want you to do it there in class, so that you have the experience and the exercise to actually do it. Okay, so any question? I think that's all that I want to cover today. We will continue with the other lesson, or the following, let me see, the following slides afterwards, which will be covering, let me see, distillation, other distillation, as well as the core calculation, which is the McCabe-Thiele method, which is to calculate the number of trays. Okay, so I think, if do you have questions? If you don't have
Doctor,
questions, yes?
doctor. For the Telegram, you can just delete to remove a person.
Ya, nanti dia delete daripada kontak saya pula, tak kan?
Tak.
Okay, thank you. Siapa tu? I know lah, Azwan.
Azwan.
Okay, thank you, Azwan.
Welcome.
Okay, any other question before we go? Macam mana dia pergi ke saya tekan lama-lama? Oh, remove from group. Tak boleh, kalau saya tekan delete nanti dia delete contact lah. Saya kena tekan lama-lama, Azwan. And then akan ada keluar
When
remove.
I press delete, dia just buang je daripada group tu. Contact still ada.
Ya ke? Tak apalah. I just press lama dia keluar pula remove from group. So Telegram tu is quite different from WhatsApp, but just it's useful because it automatically save into our phone. Okay, so kita boleh set lah anyway. Nak set automatically save pun boleh juga. Alright, so any question for today's lesson? Do you understand what distillation is? Tu yang simple je. Nanti the hardcore of it is, let me show you the slides again so that I can. Yang hardcore-nya this one, the McCabe-Thiele method. Okay, so kita akan buat the graphical method on how to, you akan, the graph that you draw for benzene toluene tu simpan because you are going to be using that graph over and over again in different question. Okay, so nanti you akan buat benda-benda ni semua. How to, this is also benzene and toluene. So you'll be using the same plot. Nanti you akan buat ni semua ni. Nak kira number of stages. There's a lot of steps to do this. Nak buat Q line, nak buat feed line. And then last kali baru you do the stepping off. Nak buat Q line lagi apa. This is a lot of things. This is the core. Lepas tu baru you buat benda tu. Wah. The stepping off, lepas tu tukar line daripada enriching kepada stripping. This is a lot of things for you to digest. But I'm not gonna go over it today. We will go through this, I think maybe just an introduction on Thursday. Sebab kita akan cover first the other types of distillation here. Tapi before we go, saya just introduce sikit lah this simple distillation method ni is just okay, before we go sekejap je. Oh, tapi ada 5 minit je. I want you to read on this ya. This is simple distillation method. Just like a simple separator, there's no plates or whatsoever. You just have a heater to heat your vessel over here. There's no, this is like what I said is a flash distillation. Okay, so single stage binary, they akan heat and then the liquid mixture partially vaporized. So the vapor will be allowed to come into equilibrium with the liquid and then separate it, and then you can do your balance as input equals to output, and then you dapat macam ni. So this is also unknown X and Y. You will do it as solve it simultaneously between equilibrium line and overall material balance, similar to the example that you did just now. This is for simple distillation method, which is also called as a flash distillation. And then yang ni simple batch or differential distillation. Ini just another type, okay. Dia slowly boil and then vapor withdrawn rapidly to condenser. Dia boil, and then once you get the vapor, it will go straight to the condenser. You terus get the liquid that is produced from the condenser. And this is what you call a differential distillation. So you will calculate this using the XY plot as well, using the area under the curve. Maybe I'll just go over that again with you. But this is not usually the core business that we put our focus on in distillation. So what we are going to go over on Thursday is this make it clear method. If I can finish it in a day or in an hour. Otherwise, we will continue on Sunday. Okay? Ada kelas lagi at 4 tak? Do you have class at 4 o'clock? You have? You have class at 4 o'clock? Ada ke? Don't see you answering. Yes. You have class? Oh, ni jawapan tadi. Oh, no more class today. This is your last class? No. Okay. Right, that's all right. So everyone doesn't have class today because maybe next time if we have more to cover on Sunday, we will just have straight until 5 and we will have no class on Thursday. So that way it's easier and a lot more can be covered in 3 hours rather than, okay, I have to stop now because you have other class at 4 and then we'll continue on Thursday and the momentum is not there anymore. So everyone doesn't have class at 4 on Sunday? Memang tak ada? Semua. I want everyone to tell me whether sesiapa yang ada kelas on Sunday, type yes. Otherwise, I'll just assume you don't have class on Sunday at 4 p.m. Ada tak? So I don't see anyone typing yes in the chat box. So that means no one has class, right? On Sunday. So anytime, if I need the time to go over 4 o'clock just to finish the topic, I can do that with you guys. Are you okay with that? So then you won't have class on Thursday. Easier that way, right? That way you will have your Thursday to you. And it's actually the end of the week already and there's a lot to do. Okay ke tak ni? So on every Sunday, if I think that I need a little bit more time to cover the topic, I can go more over 4 p.m. right with you guys and finish it. And if we finished it, then I'll just let you go for Thursday. No class on Thursday. But for today, I actually have things for me to settle for today. I can't have class for more than 4 p.m. with you. So I think I will leave you to that for today. Okay, so I'll start recording now. So for those of you